Gotcha.
Oh, and also, I don't have a grade in for 103, and there's like 2 of it in the grade book. But,
There's 2 of them in the grade book?
yeah.
Okay.
And I submitted on Google Classroom.
Okay. Let me
It's because I wasn't here for like the actual test day. I submitted on the test
gotcha.
day. So,
Yeah. I forgot to grade everybody else's anyway, so that'll be an easy fix.
Mr. Townsend,
Yeah.
what is the policy on if something's due today, but I don't have my backpack to turn it in?
What is due today?
Well, it says, oh wait, no, that's homework, never mind. I'm in the wrong section. Never mind. Is anything, oh, what you just said.
I mean, the policy would be you should have brought your backpack.
Okay, fair enough, yeah. Well, I never take it out of my car until the start of spring break because I want to on the road trip.
Earl should be here. Lincoln's out today. Sam
Like
Grace.
sitting in the rain in my car 5 minutes before advisory. Then I don't have backpack. Pretty relatable.
Grace.
Advisory's the best one to
Grace. Spencer. Sebastian. All right, good morning. Welcome back, guys. I hope you enjoyed your break. I think we've got maybe one 3-day weekend left for the rest of the year, the April 8th, the Eclipse Day. Short of that, the 8th, we are pretty much straight through for the rest of the year. So before we went to spring break, we had started a couple of the topics from the last unit. So the 2 topics we had looked at was L'Hopital's rule, and we looked at that one 2 days before spring break started, or 2 class periods before spring break started. You can see under homework, I'm asking you to finally turn that in. So if you didn't get that finished before spring break, and then you still didn't do it after or during spring break, then you need to finish that up to get points. I will still ask for the area between 2 curves one, but I will ask for that next class. So I'm trying to give you about 1 class of delay there. So we are going to look at really 1 new topic, but 2 different methods. Volumes from revolutions. One method is called a disk method, and one's called a washer method. The washer method's really just like the disk method twice, and then you use subtraction. So it's important that you really understand the disk method. Also, as we get close to our AP exam, I'm going to start to throw a lot of small 1 to 5 question mini quizzes at you guys at the start of class to make sure that you know some of the stuff, and if you don't know it, then to review it. So usually just 1 or 2 topics at a time. So that's under the upcoming assignments. The one next class will be specifically on the 2nd fundamental theorem of calculus. And in fact, I will tell you where you might want to look back at your binder for that. That would be number 78. I'll type this on here, 78. So, again, you guys have been using that. I think you know that, but if you don't, make sure that you look over 78 and be prepared for a 1 to 5 question quiz. Now, these mini quizzes don't hold a lot of weight. Obviously, I'm not going to make it a 50-point test or anything like that. It'll be anywhere from 1 point to probably 5 points, but when I give you a bunch of them, it does add up over time. So potentially you might want to spend 5 or 10 minutes looking that over. Okay, so our plan today, one of the handouts you picked up is over the DISC method. So we're going to look at those notes real quickly and talk about the calculus behind that. And then I'm going to pause for about 10 minutes and let you try the Khan Academy over that topic. Then, finished or not, we will go and do the notes on the washer method, which again is really like the DISC method twice with subtraction sign in between there. And then I'll give you another 10 or 15 minutes to try one Khan Academy on that. And then, finished or not, we will do one more practice FRQ that doesn't have to do with this unit, but has to do with AP review. And then any other time that you have left over, you can go back and finish 109 and 111 if you need to. All right, so with calculus and stuff we've done this second semester, we have talked about things like this, where if you want to find the area under the curve between A to B, you can integrate from A to B. You can integrate the function, and that is one way to determine how much area something has. Even if the area has some curvature to it, where it doesn't fit just a nice, neat, plain geometry formula like you learned in geometry and for the ACT. But now what we're going to do is we are going to figure out how to figure out the volume of shapes like this. Shapes that don't just fit a nice, neat geometry formula. You don't get to just plug in a couple numbers in your calculator and hit enter and it tell you the volume. We have to use calculus to do this. So the way this works is we're going to add up a bunch of stuff. Specifically, integration. Integration adds up a bunch of stuff. Unlike area, though, where we're going to add up a bunch of rectangles. So when we do length, like this would be the function. This goes here. The width, the width is actually the dx part, the change in x. So when we're doing this, it's really length times width. But to get a 3D shape, what we're going to do is we're going to take this, take like a spot, and we are going to rotate it around the x-axis or around the y-axis. So as it rotates around, it creates a circle. And then right next to that, we rotate that around and it creates a circle. And then you go next to that, and you basically just do this an infinite number of times. The only way to add up an infinite number of things is with an integration symbol. But because I want a bunch of circles, this is where it gets the name DISC. DISC are like circles. We want to use the area of a circle formula. I want to add up an infinite number of circles. So we're going to do pi r squared. And then we'll just replace r with how big the radius is. So for this one, the radius goes from here to here to here to here. So that has some kind of connection to the function. But all it really means is we're going to add up an infinite number of circles, and when you add up an infinite number of circles, you end up with a three-dimensional shape. Okay, so down here, question 1, I've got one of each that I'm going to do for you, and one of each I want you to try beforehand. This is a typo though, this should say DISC method. Alright, so first let's go ahead and sketch these. We need to have a little bit of a visual at first because determining the radius is going to be the hard part here. So here is y equals 0. It's the x-axis. And then x squared minus 3. Something like this. Now for this one, or the first two, we are going to rotate around the x-axis. So we're going to take this area that's trapped in between these, this, and we're going to rotate that area around the x-axis. And as that two-dimensional area gets turned three-dimensionally, the shape that it creates ends up being a three-dimensional shape that we can find the area of. All right, so first thing, because this says x-axis, we want to integrate with respect to x, and the bounds need to be x values. So you can solve for where these two lines intersect, and you could solve where these two lines intersect, and by that I mean set them equal to each other and solve. So I'm using x values because I'm rotating around the x-axis, so I'm using dx. Okay, you have to remember that we're adding up an infinite number of circles, so it's going to be pi r squared. And the r, this is the part that requires the most thought. You've got to be careful here. So if I zoom in on my picture to try to show you, right here, this isn't going to turn as much. Like this is going to be a smaller circle. When I take this point and rotate it around the x-axis, it's not going to go as far up. The biggest point would be this one, and when I rotate it up, it goes this way. And when I rotate maybe like right here, it's somewhere in the middle. So you have to see that the radius changes sizes depending on what x is. But with our picture, and this is why you need a picture, I can visually see that this links the radius, this links the radius, this links the radius. All of these are the y value of this function. So the radius is actually x squared minus 3. That's the length of the radius. Again, it's not always the same radius length. It depends on what x is, so that's why we need x's. Now, to help you in the future, in one of the next few questions, because this is dx, this stuff better be in terms of x. If this was dy, I would want this stuff to be y's, not x's. Okay, and we don't actually need to integrate it. We're just going to practice setting it up. So, even when you do the Khan Academy, I'm going to welcome you to just throw the integration in your calculator. Let your calculator do the integration. Because that's not the point of these. The point of these is to try to set them up. Okay, so I'd like you to try this once now. So graph both of these. Think about why I did this graph and how it helped me. It's got to be integration. Think about whether it should be dx dy, what you think the balance should be, why is there pi here, how did I come up with this. So go ahead and try it and see how much of that you can piece together from that one example. Everybody 30 more seconds to try to be same spot. Okay, So the parts of this that should have been pretty quick and easy is because this says you're rotating it around the x-axis. You should have been integrating dx. Because you're rotating it around the x-axis, the bounds of integration should be the x values. So if you've made a picture, it's a little easier to see. It's from -2 to 2. If you don't have a picture, / you don't want to make a picture, you could set these two things equal to each other. If y equals this and y equals that, then they must be the same. And if you solve that, you get -2 and 2. So that's a way you could do that. Every single time, the disk method and the washer method is always going to be an infinite amount of circles. So pi r squared. The only thing that you really should be slowing down on some, maybe not on this one because it was the first one that you tried, is thinking about what r is in terms of x. And again, as you do more of these, you may think that the picture is less and less necessary, but I suggest you sketch in a few of these. This is the area that's trapped in this stuff. So when I rotate this point, it would make a circle about this big. When I rotate this point, it would make a circle about this big. But the point that the picture might help you on is you can see that this is the radius and this is the radius. The radius is always the y value of that function. -x squared plus 4. So if you integrated from -2 to 2 of -x squared plus 4 squared times pi, then you would have the volume of that three-dimensional shape. Now again, the radius is kind of the hardest part, and that's where your picture is hopefully going to help you, because you can see the radius, you can see how it's changing, and it's more likely that you can see that it was y in these questions. My advice would be try to make your picture a little bit bigger though. I made mine so small it's kind of hard to see it. Okay, so the disk method, I've got another typo here. The disk method, now we're going to go about the y-axis. So a lot of the same idea, but because this is along the y-axis, we're going to integrate dy. I'm still going to do an infinite amount of circles, so it's still going to be pi r squared. I recommend that you put that down because a lot of times students will forget the pi. Pi r squared is just a bunch of circles. Because it's dy, I need to list the limits of integration needs to be y values, and this needs to be in terms of y. So again, I guess the picture is sometimes optional, but if I took the x-axis, the y-axis, and -x plus 8, this is the area that I'm trying to rotate around the y-axis. By the way, you don't have to draw these little circles like this, but you'll probably see them in some questions. This is just a way to show which direction we're doing. Okay, so because I have a picture, I can visualize this a little better. When I take this point and spin it around the y-axis, he would be about this big. Down here, this point would go a little further. This would be the biggest of them. So with your picture, I hope that you can see this is the radius, this is the radius, and this is the radius. What do we normally call this length?
X.
Right, this is the x value. It's going this far to the right, this far to the right, this far to the right. But, so if this is x, and this is x, and this is x, x is what's changing, I don't want to just put this stuff down here. This doesn't make sense. This is x stuff, and it's supposed to be in terms of y. So, what I could do is I could subtract the 8 over, and then divide both sides by a negative. That is also x, but it's x in terms of y. So the radius was always x. I solve that equation for x, and it's the same as 8 minus y, so that ends up being the radius. 8 minus y, 8 minus y, 8 minus y. In fact, if you're not sure, you can test a couple points. You know, when y is 0, this would be 8. When y is 0, the radius is 8. That makes sense with my picture. When y is 8, the radius would be 0. So when y is 8, it's right up here, and the radius would be 0. So you can test a couple points if you feel unsure about that. But that, oh, I forgot something. I need the bounds as well. So because we're doing dy, you shouldn't be using the x values, even though you would accidentally get it right here. It's from the smallest y value to the biggest y value, 0 to 8. So what is consistent is it's always pi r squared. If you spin it around the x-axis, it's dx. You spin it around the y-axis, it's dy. If you spin it around the x-axis, the limits of integration need to be the far left and far right values. If you spin it around the y-axis, it needs to be the bottom y value to the top y value. But your radius, again, is the hardest part, and that's where the picture hopefully helps you see that that was x. For all of those, the distance from here to the right is what we normally call x, and this is what x was equal to in terms of y. You need these variables to match. If this is dy, this should be y stuff, not x stuff. Okay. So if you would, go ahead and try one of them to see how much you can get correct. And again, a lot of this should be pretty quick. Part of it you need to slow down on, but and don't actually do the integration. We're just setting it up. This is supposed to say x equals 0 too. Sorry, it didn't print off. Okay, so the parts that should have been pretty quick here is you should have just about instantly said it should be dy because of the y-axis. Pretty much instantly, you should know it's going to be pi r squared. What's going to take a little bit longer are the bounds. So the bounds can either be found by doing a good picture or by setting these two equal to each other and solving. But since this is dy, I want to go from the smallest y value to the biggest y value. So not x values, because I'm not spinning it around the x-axis. It's not 0 to 5, it's negative 5 to 0. And then really your last hurdle, well, I guess there could be two more hurdles, is thinking about what is the radius in terms of y. So again, your picture can kind of help you see this was the radius, a little bit bigger, a little bit bigger, a little bit bigger. But this distance from the y-axis to the right is what we normally call x. X to here, x to here, x to here, x to here. So it's to x of this function. And what was this? X minus 5. So you should not be plugging in x minus 5 as your radius. This says dy, This stuff should not be X stuff. It needs to be Y stuff. So add the 5 over. X on that function is the same thing as Y plus 5. Y plus 5 is the radius you want. So that integral would give us the volume of that shake. And to be fair, that one's kind of silly to do this way because this is really just a cone. I mean, we have formula for volume of a cone. It would be a lot easier to do that, but this would be the same thing. And again, this is going to build up to washer method. Okay, so is there any quick clarification you would like on over any of these 4 examples? Okay, then I want to give you 10 to 15 minutes here to go ahead and try this Khan Academy. If that's not enough time, you should hopefully have some time at the end of class. Again, don't do any of the integration by hand. If there's any integration that you have to do, just let your calculator do it. I'm more interested in you practicing setting these up. But finished or not, 10 to 15 minutes from now, we're going to look at the washer method and do its notes. So. And I have 2 of them assigned to you. Make sure you're picking out the disc one. I haven't shown you the washer one yet. Looks like a lot of these are set up to, the answers are set up where you can just pick out the way it's supposed to be set up. But there are a couple that actually want you to integrate. So again, feel free to use your calculator to do the integration. Of course, if you miss one, feel free to click the start over button. But I ask that you please don't just guess to as a way to start over. Don't just rush through the last ones if you need to start over. Click the start over button. I will probably try to collect the most missed questions for us to talk about as a group in the next class or two. questions, especially the ones that actually want you to do the integration, I think they all say leave your answer in terms of pi. So that means you should not put pi in your calculator, but leave pi in your answer. Shouldn't be putting in a decimal there. It should be like something pi.
Second try, Mr. Chapman. You believe it?
Second try what?
The Khan Academy sign.
Good job.
I didn't hear you say let the calculator do it, so I just guessed. And I restarted after the third question. That was before you said not to. I restarted.
All right, you guys are about 7 minutes in, so again, I'm gonna give you a little more time, but if you don't finish, you'll need to go back and finish after we do the next set.
What did you do for integration?
Lots and lots of unfun chores.
Fair enough, fair enough.
Spring break is not usually fun for me.
No, I'm sorry.
Adult stuff, taxes,
Oh, I did those.
fixing toilets.
Fixing toilets. Did you like replace one or just like unclog them?
I had one that how much do you know about toilets?
Well, I know quite a bit.
The sill on the bottom of the toilet was broken.
Oh, okay, so you had to pull it up and put it in.
Yeah, it was like leaking water under my tiles and it was squishy to step on.
Was it like the clean or the dirty water?
Hmm?
Was it the clean or the dirty water?
It's just a bunch of stuff like that. Dryer vents,
I need to clean mine.
HVAC.
Well, at least you got it done, right? Better than doing them after school on a rainy day, you know?
That is true. I'm glad that I have that stuff done.
Did you have like a list of things, or did they all come up during school break?
I had enough things to do that I just did them as I thought of them, and I stayed busy.
Did you go out to dinner at all, or no? I feel bad now.
Hmm?
I feel bad now.
It's okay. I mean, I could have gone out to dinner.
Yeah.
Okay, I'm gonna give you 6 more minutes, which is the full 15. The reason why I'm trying to give you a little more time here is because if you don't understand this method, you're gonna struggle with washer method. So, I know a handful of you are already finished, but just wait patiently, please.
Bless you.
just about 2 more minutes, and then we're going to move on. Again, if you're not finished, you will have more time to go back. I won't put the grades in until the start of next class, so. Okay, go ahead and finish up the question you're on, and I'll pause for a second to let you catch up, but don't start another one. Okay. So now let's look at the washer method, which again is like the disk method and subtraction. So to me, this is really very similar logic to what we did for area between two curves. We did this right before break. If we can integrate f of x, and it gives me the area under f of x to the x-axis, that would give me all of the red area. And then if I integrated g of x, that would give me all of the area under g of x, which would be the purple area. If you want to know the area that's trapped between those two, you just find the area of the whole thing, the top, and then subtract the area of the bottom. So this same thought process, if we can take the big picture and then subtract off how much of it's not supposed to be there, then that's what we're going to be doing with the washer method. So what I mean by that is, if we can take this big, if we can find the volume of this big shape using the disk method, we would get one number. And then if it's hollowed out, so there's some volume missing here, but if we can calculate the volume of this with the disk method, then the leftover stuff, the volume that we actually want, would be by taking the volume of the whole thing and then subtracting off how much volume is missing. So it's basically disk method for this, the whole picture, the disk method for how much is not there, and then take it away. So we have to do that 2 times. So a lot of my strategies are still going to be in play here. So let's go ahead and graph this. Again, the better your graph looks, the easier it's going to be to understand what you're doing. Okay, so if I graph all three of those, this little triangle is the area that's trapped in between those three, and we're going to rotate this one around the y-axis. So some of the stuff that's still going to be true is, because we're rotating it around the y-axis, we want dy. Because we're rotating it around the y-axis, we want the smallest y value and the biggest y value. What is the biggest y value? Okay, up here at 0, I agree. What's the smallest y value?
6.
Wait, doesn't it go down to -9?
That's not part of the enclosed area.
Very good. It's where the area starts being trapped together, which is at -6. So if you're not careful, you might think it's -9 to 0, but the entrapped area is from -6 to 0. So again, that's where the picture helps. Again, sometimes you're given a picture. I know a lot of the Khan Academy questions did have a picture. But now we're going to do pi r squared. And then I'm just going to combine these into one big integral instead of two separate integrals. I'm just going to push them together. So this is usually referred to as big R and little r. In fact, a lot of times on FRQ scoring, one of the points is you showing that it's set up this way. So the big R is going to be this, where if I take the outside points and rotate them around, again, we're just doing circles. So this length, what do we normally call this length? From here to here, here to here, here to here.
X.
X. X for this function. So solve this for X. And that would be the big R. Big R would be y plus 9 over 3, or if you'd rather, 1/3 y plus 3. That's the big radius, that's to the outside of the enclosed area. But now to understand why there's a small r that we're taking away is that if I spin this area around the y-axis, it's going to create a hole in this shape. Again, I know my picture's not the best. This is a little better visual of that, I think. But when I spin this around the y-axis, from here to here, here to here, it's creating a cylinder in the inside. And what is the radius of each cylinder? 1. The radius of this is always the same thing, so it's not in terms of x or y. The radius is just always 1. Big R squared minus little r squared. Now again, this is the same thing, and I would like you to write this down once, and then you can choose to do it or not. But this is really like pi r squared for the big one. Take away how much is missing. Take away pi r squared of the smaller one. I just like to write it as one statement instead of two separate integrals. That's how you really should practice doing it. But if you want to write it like this for a little while, that's okay too. I understand why. So the big overall shape is a little too much volume. Subtract how much volume is missing in the middle. And this is what's called the washer method. Do you guys know what a washer is? Like when you build furniture and stuff? Okay, that's where it gets its name. Because a washer is like, it's like a disc, but it has a hole in the middle. So, all right, so if you would go ahead, and I've got just one of these for you to try as guided practice. So go ahead and try to make that picture for number 2 and try to set up the integration as one big statement. See how close you can get. Now, similar to the disc method, I think some of this is pretty easy and quick, but specifically the radius or radii, you probably need to slow down a little bit. Those are a little bit trickier to get, depending on how good your picture looks. So, So I'll give you a few minutes to try it. I'm going to go ahead and sketch it while y'all are starting. Okay. Let's see how close you got. All right, so again, the picture has lots of benefits. So if the picture's not made for you, if the functions are realistic enough that you can graph them by hand, you probably should graph them by hand. So I can tell that if I rotate this around the y-axis, it's going to create some empty volume inside. So I know this is considered a washer type problem instead of a disk type problem. You don't ever need to differentiate between the two, but it does make a difference in how you set it up. So I'm going to combine it into one big statement, pi r squared minus pi r squared. Always big radius first, small radius second. Since you should have been rotating it around the y-axis, you should get a dy pretty much instantly. To think of these y values, again, you could algebraically set the correct two things equal to each other to see that this equals each other at 4 to 9. 4 to 9. Smallest y value to biggest y value. And then for your big radius, that would be the outside points not like that. Like those. So this radius is x, this radius is x to this function x squared. So why can I not just put x squared there? What should be obviously wrong about that? Yeah.
It needs to be in terms of y.
Okay, how do you know it should be in terms of y?
It's rotating around the y-axis and dy.
Sure. Yeah, so the dy tells you that this stuff needs to be y's, not x's. So you should have solved this for x. X is the same thing as square root of y. That's the big radius. And then the small radius is this one, and it's always the same size. The small radius was always 2. So that gives you the volume of the big outer shape and takes away the missing volume that would be created in the middle. That's what you were aiming for. Okay, do y'all need to ask any clarification on that? You at least see where your mistake was? Okay. All right, so now let's look around the x-axis. So really the same idea. In fact, I think you could probably handle it from here, but let's do one of each here. Okay, so graph, 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 enclosed area, the area that's trapped between all three of those. But this time I'm going to rotate it around the x-axis. So instantly I know it's a dx. Instantly I know I should be using x values for the limits. So this and this are equal to each other. That would be these two. Again, if you can't see from your picture, just set them equal to each other and solve. That would be when x is 2. That's what it looks like, but I just wanted to double check. And then this would be when x is 3. I know that one for sure because I know this line is x equals 3. Now, when I rotate this, there's going to be a gap in volume right here because all of this area is not hugged up next to the axis we're rotating it around. So in this case, the big radius is going to be to the outside, and that radius is always 3. Whereas this time, the small radius is going to be this. It's going to be that part, the hole that's created if you rotated this around. And this distance is what I would call from the x-axis down or up. This distance is what I would call y to this function. Both of those are y, and that was 3x minus y, or 3x minus 9. Now that's a good way to write that because this is dx, so this stuff should be in terms of x. I did skip over one thing though, one of the more common things to overlook. Right, you need pi. Remember, these are a bunch of circles. Pi r squared minus pi r squared. If your pi is not out there, it's not correct. Now, I know multiple choice when you're just trying to pick out which one's correct. Most of them are there, so it's hard to miss it, but sometimes that's not the case. Okay, so hopefully I've convinced you of when you need dx, dy, what the variables are supposed to be, where the bounds are supposed to be, and that's it's really just area of a circle, infinite number of circles. And I hope that I've convinced you that the picture really helps you dig out some of that information. But I need you to try it one more time. For one more, I'll go over with you and help you hopefully quickly make some corrections. So please try this question 4. And then we'll compare work. So the quick parts, rotating it around the x-axis is dx, and then either visually or algebraically, you should be integrating from 1 to 2. That's where the trapped area is. The big R, it's always big R squared minus little r squared. The big R squared would be from the outside of this. So you should be trying to look at this length or this length, which are both y, in the y equals x squared. So the big R should have been x squared. And then the small y, or the small radius, sorry, should have said the small radius, would be this volume gap that it's creating. So from here down, here down, here down, those are always the same, and those always have a radius of 1. So this integral is what would give you the volume of that 3-dimensional shape by rotating this 2-dimensional area around the x-axis, even with the hole in the middle. Okay, any quick clarification you'd like on 3 or 4 on this page? Yes. Chris?
So I'm confused. If it's revolving around that, like, I'm confused about the space that's between.
Okay, what is your question?
Where would
Where would what be?
this radius of the space in between the shape?
That would be these little the red circles I have.
So it doesn't have to be all one.
I don't know what you mean by all one.
The same radius.
No, oftentimes it's different. I mean, most of these were different. Like this one had a radius of 3. The outside was always the same, but the inside changed because here the radius is big, and over here the radius is small. So you can at least see it's dynamic. It depends on what y is, or it depends on what x is.
So sometimes the outside is a cylinder and the inside.
Correct, yes. Yeah, it can be either way. That's where, again, I know my pictures are not great, and your pictures are tough too, but the pictures give you a visual to what the big radius is, or what the big outer part would be and what its radius is, and what the smaller inner radiuses would be. And then, since that's the hardest part of these, that's where I just really think a picture helps. Yes?
You just do it without figuring out the radius and just take the absolute value of whatever your answer is.
Absolute value of what?
The result of the integral. If you did,
Like in this one, what would the integral be instead of this?
well, if you put 3x minus 9 squared minus 9, and just take the absolute value of the result of that, it's basically the same thing.
Yes. The problem with that is when you say absolute value, they may ask you to do this on your AP exam, integrate by hand. And if you start throwing absolute value signs in and you don't have a calculator, you might be stuck. So that would be, I guess, the only downside. But yeah, you're right. A minus B is the same as the absolute value of B minus A. So. Okay. I guess I will let you pick here. So I'm going to give you guys another, let's say 20 minutes this time. So if you did not finish the disc method, Khan Academy, you're welcome to start it first if you want to, or you can move on to the washer method. If you finish the disc method one, you need to move on to the washer method one. And again, I'm going to give everybody 20 minutes to try to get to the same spot, and then we'll be done practicing this for today. I will have you practice this more, and in fact we actually need to do these same questions again, but instead of rotating it around the x-axis or around the y-axis, sometimes we rotate it around like x equals 2 or y equals 5, around different lines. doesn't really make any difference in the questions and how we approach them. But we do need to practice that. And so we'll practice some more of this. So you don't have to feel like you have this mastered by the end of today, but you should have a good understanding of what we're trying to do and what your approach should be. And again, we're getting pretty close to you have seen all of the stuff that's on your AP exam. So just a couple more question types, and then it'll be all reviewed from there. Again, feel free to do all the integration in your calculator. I know you can do the integration if I gave you more time, but the focus is really just on setting them up. And again, at the end of this 20-minute timer, I will ask you to put this aside for a few minutes so we can do at least one practice FRQ today that's not related to this stuff.
Yeah, too small for one, that's why it's too large for one. Wait, 120, I think. 1.21. So 2. No, it's 2. Yes.
Okay, I changed the agenda just a little bit here. It was gonna be kinda tight to get in one practice FRQ. I think we probably could have done it, but we wouldn't have had time to talk about it at all. So I will give you the rest of class to work on these two Khan Academies. But if you don't have them 100%ed, I need you to keep trying them and be finished before class on Wednesday at the very latest. And under homework, remember, I am asking from the circuit that we started on 2 days before your break started. So that one should be finished, but I have not asked you to turn it in until now. So that also needs to be turned in between now and Wednesday. And finally, your short 1 to 5 question, 1 to 5 point mini quiz next class. You might want to look at number 78 in your binder. You might want to add that to your homework list too. Now again, I know 1 to 5 points doesn't sound like a lot, but they will be major points, not minor points. And over time, those will add up to be quite a bit. So if you just wing it every day, you're going to be missing out on some points that you could get if you just reviewed it for a moment. And again, I'm just trying to force you to review small chunks of stuff so that it's not so much right before the AP exam.
Look at this, Mr. Jones. So, answer is 15 and 1/3. We typed it in.
I think it probably just doesn't do it correctly. My guess would be that you may be able to, but you maybe didn't type it in the way you thought. But the proper practice is your thing. Now, if you had just said 15.3 or 30 or something like that. Okay. And of course, as always, you guys are welcome to do these Khan Academies as many times as you need to. It's great if you can get them on the first try, but it's more important that you get it eventually.
Because if you're taking this 2D area and something else affect all of this, the outside of the space.
Oh, so you're subtracting this curve. Okay.
When you rotate this would be the very small, this would be the big one, because this is the one that's all the way down. These pictures are helpful, but the fact that they don't show down here, you can't see, like, it actually goes all the way down here.
Also a good idea, if you think you might need some help on this, you might sign up for prime time on Tuesday or Wednesday. I'd be happy to help you. But I need you to be caught up with everybody else by Wednesday, so. And y'all still have 20 minutes since I took that last part off our agenda. It was a little too rushed.
Which one's the bigger one? Which one's the smaller one?
Well, what are you rotating around?
The y-axis.
Okay, so the one on the right would rotate further than the one on the left.
I see.